So first of all, thank you all for attending my talk. My name is Igor Kopestenski. I work in UC Louvain with Professor Peter Van Rooij and Per Streitzinger from GRiSP in the context of the LightKone research project. And I currently study distributed systems on IoT edge networks. So first of all, I'd like to start this talk with a quote that's helped me a lot reasoning about distributed systems. It's about the mapping that exists between processes as they are in Erlang and how we should actually see them in the real world. And the rest of the quotes, actually having fun, I think is equally as important because there's a lot of fun to be had in Erlang. So I'd like to start by defining actually edge computing. So there's a lot of kind of this buzzword effect around edge computing, and most of the cases when people say edge computing in their product brochures and solutions, what they actually mean is edge gathering, because everything kind of still exfiltrates data from the actual edge to pull it out, and the processing is still done at higher layers. So the computing part and the storage part being brought closer to the location where they're needed, this is to reduce congestion of networks and reduce latency and improve performance overall. And it's a new emerging computing paradigm that actually is still kind of this is also from Wikipedia, by the way. There's a lot of things that are left to people's imagination about how to design their systems when looking at this kind of architecture, because there's literally no standard at all for edge computing. People just do the best they can. So I'm not going to go too into depth into this, because the problems are actually quite numerous, and there's probably way more than listed here. But the main thing is that IoT devices are going to explode in the next 5 and even 10 years. And at the edge of networks, there will be so much devices that will be unreliable, that will be sometimes online, sometimes offline, that will move, that will have limited resources, they will maybe sometimes even energy sensitive, and we still need to do something with them, because like it's impossible to handle all this amount of data and traffic that it would produce otherwise. And it needs to be autonomous, because it's impossible to coordinate with a centralized architecture something like 75 billion IoT devices by 2025. And so in 2009, there was as much devices connected to internet as humans. Today, it's about nearly four times as much. It's going to be 10 times as much in 5 years, and probably much more in 10 years. So it's physically impossible to even cool data centers that would be big enough to process this data from sensors, from actuators to monitor smart things connected to internet with this same design architecture where everything goes through gateways to points of presence to cloudlets, foglets, edge clouds. There's a lot of, again, buzzwords that always mean the same. It's just servers that get bigger and bigger up to AWS somewhere. So how do we solve this problem? Nah. So the approach that I would like to propose is just to start by thinking, why should we actually draw a line between the edge and some other devices that are even further on the edge, but we don't like to actually do computing and storage on them because it's complex. And basically, it's just forwarding the current problem to a posteriori point in time. Because if there are, let's say, far more IoT devices than expected, basically the edge clouds would have the same problems as the regular clouds have today. And of course, these devices don't have permanent internet access and may rely usually on some single points of failure, like gateways for internet access. And as far as I know, the best that's offered by industry today is systems that actually store data locally and wait for internet connection to be able to do anything, and if it's too long, they shut down and it's done. So if this situation is even worse and gets highly unreliable and highly dynamic and mobile and whatever worst case scenario we could imagine with 50 billions of devices at the edge, drawing this line with edge cloudlets being the edge is not a viable model. So the LightKone project has proposed something called LIRA. It's the LightKone reference architecture. And it basically sums up how all the components that have been developed with Erlang can always form overlapping layers at some point so that the whole spectrum from end to end is covered. And the framework I developed is at the place of this tiny blue puzzle piece, and it's called ACLIS. So the new concept that LIRA introduces is also called lateral data sharing. So usually what you would see is these red lines from sensors, points of presence, etc. These are upstream data flow that simply go to data centers and results come down back. With both horizontal and vertical data sharing, it becomes much more easier to reroute and relocate resources and data so that whenever some component in a network is able to either process something on its own or delegate what it cannot process to others, it's doable both north side, south side, east and west side, which doesn't currently exist as an implementation. So, to sum it up, the LightKone project targets general purpose computations on the edge with distributed and convergent storage from data centers to sensor nodes. So the points where data is actually created, basically, the furthermost devices from the epicenter of networks. And this final layer needs to be autonomous because it's so unreliable, but it still needs to be able to cooperate with the rest. And all of that, we want it simultaneously and to be all reliable. That kind of makes it quite challenging. So the scope of the framework is to allow IoT nodes to have zero config clustering, so being able to discover themselves, to sense in a cooperative fashion, have inference on multiple dimensions of data, for example, deducing new knowledge from sensors that are not present on some node but come from somewhere else, and offer also a general purpose computation API, basically, that allows these nodes, whatever their processing capacity is, to be treated as cores that can perform any kind of computation. And also, I want to provide a maximum fault tolerance, even in hostile environments. So, my current prototype runs on the GRiSP embedded system. So, this is what I have right here with me. These little blue modules are sensors, can be actuators, and are used to produce the IoT data. So in terms of capacity, my professor always says that a GRiSP system is more or less same power as a high-end laptop from 20 years ago, which is, I mean, with Erlang 20 years ago, very, very good stuff was done, so why not with GRiSP? So the sensor I have on this one is actually looks like this from up close. So you can see the pins going left to the board and the actual ambient light sensors being attached to it. So thanks to Per Stritzinger, I have a nice way to represent the actual advantage of this board, which runs the Erlang VM on bare metal, compared to the Nerves project. You may know, for example, that still runs a tiny Linux kernel, except it just launches Erlang as its first process. On GRiSP, Erlang is the equivalent of operating system. You get to interface directly with the hardware in Erlang. So making drivers for these modules doesn't require you to know how to do low-level driver coding stuff. It's pure Erlang. All the low-level stuff is already done by GRiSP. Thank you. And my application is based on top of LASP and Partisan libraries that are its distribution and CRET components. So the choice of Erlang is basically there are plenty of reasons that make IoT edge networks match their requirements with telecommunication networks, which means they need to be highly resilient. They need to be able to respond with low latency to other nodes. Since there's going to be so many of them, if 10,000 nodes in a cluster tend to get aggregated, this means that the Erlang scheduler is a great advantage because it guarantees still low, relatively low latency where possible. Another fantastic tool is the OTP supervisors that allow to basically keep control over crashing processes and prevent actually unreliable hardware faults or user interactions that are malicious to propagate. So the LASP and partisan libraries are the two components I use to distribute CRDT data, which means that everything that's on my system is convergent. And partisan is the communication library that replaces the Erlang native distribution to support the LASP distribution. So CRDTs, I won't really cover this. I believe everyone here knows that they're pretty useful. What I'd like to show is the API of the task model I've built for Active devices, which is basically declaring a task, telling where it should execute, either on a list of specific nodes or everywhere. Should it execute once or in permanent cycles, and the function itself that it needs to execute, which can be a higher order function, meaning that it literally can propagate programs and self-contained programs with CRDTs. For example, this turns into this, and done. So hopefully, for example, there we go. I don't know if you can see, but now I've just propagated a function that allows me to hide the ambient light sensor and just make it react to changes of ambient light, which means it's like that easy. So final point, this all builds up to something like this, for example. This is something I imagined as a fully enabled beam implementation of the LIRA reference architecture I've shown in the beginning. So every component in this figure has runs on the beam and benefits from inter-process communication, mobility of functions, mobility of data, resilience, fault tolerance, everything. From IoT sensors to data centers, which is, I think, pretty good. So for future work, there's still much improvement, such as even better self-discovery of other nodes, maybe a hybrid version of the Erlang distribution using TCP and UDP, depending on the case, and belief propagation instead of exact knowledge. Thank you very much.
Thank you. That's quite impressive. Are there any questions? Okay. I had 2 questions. Yes, you mentioned the NERVS project really a bit. Are they planning to merge? Like, are they like conceptually different in architecture? I know that they.
I think Per Stritzinger might answer that question better than me. If
So we're working closely together. For example, the second version of GRiSP will also run NERVS. So we use the same hardware as an evaluation platform. But I think each serves its niche, because sometimes I need a Linux kernel because there's convenient drivers in there and I want to reuse them for some like nifty hardware. And sometimes I need real time, then GRiSP is an advantage. Or sometimes I want to talk really close to the hardware. Or you want smaller hardware, larger hardware. So there's a spectrum. But we are in the embedded working group now of the Erlang Ecosystem Foundation, and we're working really close together. So we might kind of like maybe synchronize the APIs at some point, that you can basically swap the operating system, basically.
All right. Okay, maybe one more question. Like, do you use distributed hash tables, and are there any good libraries for that in Elixir? I heard somebody mention once that there was no good DHT.
Well, my approach is to actually reduce overall use of distribution to the minimum. So whenever actually nodes need to distribute something to other nodes, it's because the end goal is to synchronize, have something consistent everywhere, enforce invariance.
Don't want to connect the entire world together.
Because it's basically impossible. No matter how you do it, it won't work with 75 billion devices. So the approach I choose is to rather try to pull locally what's distributed, process it, and only push back into the distribution what's necessary. And I haven't used the distributed hash tables for that.
Okay, well, thanks. Oh, 2 more. Okay, quickly then.
Yeah, so you mentioned that you also want to try with AGLIS to prevent misuse. So in your beautiful example of how you could call a task, an example that immediately came to mind is that you can spawn a task that, when it's run, spawns itself a bunch of more times and essentially creating a propagating virus or worm. So how does AGLIS currently try to prevent devices misbehaving in the system?
So basically, I've had in the beginning of the development of this task model, I've had lots of problems with memory overflows due to my workers doing stuff that was very stupid. So now I encapsulate these functions into processes that have a maximum lifespan no matter what, and even if they're made to run in cycles, they have a maximum heap size, and I shut them down if they grow too quickly. Because it's for the system, if there's, for example, a single articulation point in a graph with many nodes, and this articulation point connects to big components, if this node dies, there's a huge partition that might be difficult to repair. So it's far more valuable to keep the whole system being able to work rather than this singular process. But again, since it's generic, you can also choose to parameterize this and actually give maximum priority to this process, but this is left to the developer, because my goal is to only provide the platform that supports it and leave decisions to developers regarding the context.
All right. You had a question. Maybe René can already start setting up.
Thank you. That was a very impressive. I find the prospect of so many IoT devices pretty terrifying, if only in terms of energy consumption. So I was wondering, does your platform take into account energy consumption expected per task executed when deciding where and when to run a task?
Well, currently, it's something I've not been able to take into account, since I work with prototypes of GRiSP boards. They can't even sustain on their own. They need to be plugged in to power. So trying to measure and produce models for future actual production systems would be somehow a waste of time, and I believe that it's something that's ongoing work on the hardware side, but software side, it's, the lower a system can run, the more time it can spend sleeping, the best.
Thank you.
You're welcome.